Okay, I think we're going to get started. So again, I'll pass around a sign-in sheet. I did update this, so hopefully everybody's name is on it this time. Is Dionysius here?
Yeah. It's
Dionysius? I'm sorry. You're welcome. So, as I asked last time, I am going to ask you to take out your phones and shut them off. So I am going to ask you to take out your phones and shut them off. Like everybody. I find it hard to believe anyone in this room does not have a phone on them. All right. Last time when I started, the first few slides, I had said they didn't come out. So I went back and I corrected them and I drew them in PowerPoint so that the figures and text would come out. This is sort of one of the first rules of doing presentations is making sure that the technology you use to put together your PowerPoint slides is compatible with the technology you use to display your PowerPoint slides, and I failed in that regard. So the first few slides are here, and these are on Blackboard. You can take a look at them. This was really the first example that we talked about in terms of displacement and slope. Displacement is the deflection in the y direction. The slope is defined as the derivative of that displacement. The moment, which we went through a couple of calculations, is defined as this factor EI times the derivative of the slope. The shear force is defined as the derivative of the moment. The distributed load was defined as the derivative of the shear force. And so one of the benefits, as I said last time, of using derivatives is that you can determine how material is going to function before you actually build anything. The value, that factor EI, the elastic modulus, the second moment of the area, and really it's the EI, not the individual factors, but the multiplication of them, which gives you a description of how rigid some material is, and that's what we were using in those other examples. So I just wanted to point this out very quickly, and then from there, this is what I just described a couple of minutes ago. And then we got into some examples. So that's on Blackboard. Take a look at that when you have a chance. And I'm going to pull up the slides for today. Are there questions on what we talked about last time? So everybody understands everything about derivatives and slopes and moments and why we want to use that information and how we can use derivatives for that?
We're going to use the different equations like the power rule and the quotient rule and the product rule.
For what is your question? Are you going to use those?
Yes, like because it was pretty much in the homework and we were doing them last night recitation, and we were just trying to figure out like what rules we're supposed to be using.
For solving the derivatives. Well, these examples that I've been going through are from the textbook, and I'm not sure that you need any of those rules. We will get into some other examples. I'm not sure that you're going to need any of them for what I go over today. Maybe next Monday, I'm not sure. So, yeah. I mean, it's information that you'll be using over the next 4 years. maybe just not in the next 2 weeks. Other questions? Okay. So when we ended last time, I was talking about this example where you have a force applied to some member, a beam, and you're pulling laterally on that beam. And that force induces a stress, and the stress is defined as the force over the cross-sectional area. And if that force is acted over a vertical cross-sectional area, it's simply the cross-sectional area of the beam, but oftentimes the force acts at some angle other than 0 degrees. And so I went through and showed the derivation of the shear sigma sub theta and tau sub theta, the force normal to that breaking plane and the force along that breaking plane. And so that's where sigma sub theta is the force normal to the breaking plane, and tau sub theta is the force, or the shear stress, I'm sorry, along that plane. So when you apply these forces, you really want to know how are they going to break, and at what point are they going to break. So they're going to break at whatever value is greater, the sigma or the tau. And the maximum values of those are dependent only on the angle. So if you want to know what the maximum values of these are, you need to determine the value of theta that will maximize those. So again, we can use derivatives for that. And I know previously other instructors talked about identifying a maximum point and a minimum point using a derivative. The maximum and the minimum both occur where the slope is 0, right? So if you look at the slope of a line, which again is the derivative of the displacement, where that slope is 0, that is going to be a point of maximum or minimum. So this is what I just said. If we find the derivative of these and set it equal to 0, we can find that point. So we'll take the derivative, set it equal to 0, and find the angle that will give you the value of 0 in the derivative. I'm looking for, my slides are a little bit out of order, unfortunately. Let me go back real quick and see if I don't have it. So the slide that I was looking for is actually a slide that you were shown previously, and it's in your, I believe it's in the textbook. It essentially shows a curve, and it just highlights the point of maximum and the point of minimum. So we'll get to that in a few minutes. So we take the derivative of these equations, we find the value of theta when the derivative equals 0, and that will tell us what angle these shear stresses are maximized at. Okay. So the derivative of sigma theta is the derivative of sigma times the cosine squared of theta. And we're only interested in theta between 0 and 90, right? Because here's 0, here's 90. If it breaks this way, it's still 90 degrees, right? So we're only interested between 0 and 90. We don't have to worry about anything greater than 90 or less than 0. So what's the derivative of the cosine squared? Anybody have any idea what the derivative of the cosine squared is? 2 sine cosine squared? No, I don't think so. Anybody else want to give it a shot? Okay. So you've got the whole derivative there. It's the derivative of cosine squared is 2 times the cosine times minus the sine. So the derivative of the cosine is minus the sine. So the cosine squared is 2. The derivative of cosine squared is 2 times the cosine times the derivative of the cosine. So if we set this equal to 0, we can find a value for theta. And in this case, if we put in a value of 0, the cosine of 0 is 0. If we put in a value of, put in a value of 90 degrees, the cosine of 90 is 0.
To find the derivative of cosine squared theta, don't you have to use the product rule though? Because you have like, essentially you do have like cosine times cosine.
There you go. You can use the product rule. Right. So I kind of skipped over a few steps here. So using the product rule, what's the derivative of cosine squared?
Well, I mean, it's that, because it's going to make the derivative of cosine negative sine. You have a negative sine times cosine times. Yeah, I mean, I guess you look at that, but you know, the product rule.
So it might be a little clearer if you go through those steps,
Right.
instead of just memorizing that the cosine squared is, the derivative of cosine squared is 2 cosine minus sine theta. Cosine theta, cosine theta. So cosine theta times the derivative of the cosine. What's the derivative of the cosine? And what's the next step? Plus or minus? Plus cosine times the derivative of the cosine, which is minus sine. So 2 times cosine minus sine. Right. So now we set this equal to 0. What value of theta will give you 0? Well, the cosine, again, of 90 degrees is 0. The sine of 0 degrees is 0. So either one of those values will give you either the slope of the line is equal to 0 at both theta equals 90 and theta equals 0. So that either one of those could be a maximum. Either one could be a minimum. What we want to find is the maximum value. So how do you figure out which is the maximum? Here.
Plug each angle into the original equation. You identify each plug.
Okay. That might work. That might work. But there's a better way, because that's a pretty straightforward, simple equation. How can you figure this out using derivatives?
When the derivative turns positive, or when the derivative turns increase, when it goes from increase to decrease.
So if you take the derivative, the second derivative of this equation, take the derivative of that and determine the change in slope with x. If that change in slope is negative, the value that you're looking at is a maximum. If the change in slope is positive, the value you're looking at is a negative. So we take the second derivative, and this is the graph I was looking for earlier. Both of these points have a slope of 0. But if you look at how the slope of this line is changing, it is getting lower and lower and lower until it reaches 0. So the change in slope is negative. It's going from a high value to a low value. Over on this side, the change in slope is getting higher. It's going from a very low negative value, a very negative value, and it's approaching 0. So the slope, the change in the slope approaching this point is negative. Therefore, that point's a maximum. Over here, the change in the slope approaching this point is positive, and therefore that point is a minimum. Thank you. So if you want to find out which point is a maximum or a minimum, take the second derivative. So the derivative of minus 2 sigma cosine sine, product rule, cosine times cosine, the cosine times the derivative of the sine is the cosine. The sine times the derivative of the cosine is minus the sine. And simplify this to minus 2 sigma cosine 2 theta. So if you plug 0 degrees in here, is this value going to be positive or negative? Where's Daniel Fradkin? Daniel. Where? Raise your hand. If I put 0 degrees in here, is this function going to be positive or negative? It's going to be negative. Why is it going to be negative? What's the cosine of 0? How many people think it's 1? How many people think it's 0? Okay, let's go with 1. So cosine of 0 is 1 times minus 2 theta, you got a negative value. Therefore, that's a maximum. Now, we can check just to make sure, because it's possible to have 2 maximums, right, in a function. You can have a function that, let me come down here, that looks like this, right? You got a maximum, you got a maximum. So we have to double check the value of 90 degrees as well. And when you plug 90 degrees in here, cosine of 180 is minus 1, and so the second derivative is positive, which makes 90 degrees a minimum value. So the value of theta that makes sigma theta maximum is 0 degrees. And so the maximum value of sigma, the shear stress perpendicular to the breaking plane, is sigma times cosine squared of 0, which is simply sigma, which says that the maximum value of this is going to break, that shear force is going to break in the vertical direction. So it's going to pull apart this way. We take this same process and repeat it for the value of tau. And so in this case, the derivative, we're going to set the derivative of this equation to 0 in order to find the value of theta. That's a maximum. The derivative of sigma sine cosine, again, using the product rule, we come up with the derivative of this value is sigma cosine 2 theta. So what value of theta is going to give you a value of 0 for that function? If this is set equal to 0, what does that mean? So we can divide out the sigma value, set that equal to 0, take out sigma, cosine of 2 theta has to equal 0, so the cosine, the value of theta is 45 degrees because the cosine of 90 degrees is 0. Okay? Is this making sense? Am I going too slowly? No? Yes? Okay. No? Why? What would be the second answer? 135. Well, mathematically that might be right, but you're looking at the plane that the material breaks at. So we're limiting ourselves to 0 to 90 because if it's 45 degrees, it's breaking this way. If it's 135, it's essentially a 45-degree angle, right? So it would be the same mathematical answer, but from a practical standpoint, we only have to look at 0 to 90 degrees. Okay, so we know that theta, there's only one answer here, so this has to be a maximum value. No, it doesn't. It could be a minimum value. We have to make sure that that's a maximum value. Because if it's 0, 0 represents either a maximum or a minimum. So take the second derivative of the value of tau sub theta, which is the derivative of sigma cosine 2 theta, and we end up with a function minus 2 sigma times sine of 2 theta. If we plug 45 degrees in here, are we going to end up with a positive value or a negative value? Let me pick on somebody else. Where's Andy Lamani? Andy. Sine of 2 theta, which is the sine of 90 degrees because theta is 45, is minus 1. So minus 1 times minus 2 sigma becomes positive 2 sigma, makes that a positive. That's not right. It's not minus 1. Oh, the answer is negative. Okay. All right. So, yeah, so because the sine of 90 is positive 1. It's not negative 1. All right. So, because it's less than 0, 45 degrees is in fact a maximum, which means the maximum shear stress normal to the plane is going to be acting at a 45-degree angle. And the maximum value of that is going to be sigma times sine of 45 cosine of 45. We plug those in. What's the sine of 45 degrees? Anybody? Yeah. Well, yeah, that'll work. 1 over root 2, square root of 2 over 2. And it's the same for the cosine, so we plug those in and we come up with a value. The maximum shear stress normal to the plane is the shear stress divided by 2. The shear stress that's applied across the beam. All right. So with this, again, this is just a way of using derivatives to solve engineering problems without having to build anything. You don't want to put up your building and then find out that your shear stress is greater than what your beam can hold. So we want to use this information for that kind of design problem. All right. So I'm going to go through one more example, and this is a little bit longer, and it's, again, if you've got your book, if you haven't read the book, as I said last time, you should be looking at your textbook before you come to class so that you're familiar with the material we're going to be going over, and you can ask questions of stuff that you don't understand. If you haven't looked at this, you're not going to get very much out of the class. Because if this is the first time you're seeing it, you don't know enough to know what questions to ask. So let me go through this. And I like this problem because this is more related to, I'm not a structural engineer, I'm an environmental engineer, but traffic is a little bit closer to environmental engineering than structure, so I kind of like this problem. You know, you could be, and at some point some of you may be, transportation engineers who have to design a roadway, and at some point in your career you might have to make a decision, are you going to run the roadway up and over the hill, or are you going to cut through the hill in order to make the roadway have less change in topography. So in this case, the engineer sets up this design where they're going to put a roadway over a hill. If we start with the origin, which is point A or the benchmark, and a line drawn tangent to this hill at that point has a grade of 10%. On the downhill side, a line drawn tangent here has a slope of minus, or a grade of minus 8%. And this distance is 200 feet, and this point B is these are in meters. 200 meters from A to B, and 6 meters, minus 6 meters below the x-axis. And the question, there's several questions that are part of this that we're going to get to in a second. The engineer has defined this roadway to be a parabolic arc, and it has an equation of ax squared plus bx. So the first question is, what is the slope of the line for the uphill segment? And this doesn't take any kind of derivatives or integrals or anything else. What's the slope of the line for the uphill segment? Let's try Nicholas, listener. Nicholas. Nicholas? Oh. So this might be a bit of a trick question since we're in sort of a math class, and there's really no math involved in this. You want to take a wild guess? Okay. Anybody else want to take a wild guess? You're given the grade is 10%, so the slope is 0.1. The grade and the slope are essentially the same thing in transportation. When they're talking about road grades, it's the slope of the road. And since you're told that this line has a grade of 10%, that's your slope. Now, the textbook, I got to tell you, it took me a while to figure out the solution in the textbook. I found it kind of confusing. So the way I did it is a little bit different from the way the textbook did it. So, you know, whichever way you think is more clear, either way is appropriate. So if the grade is 10%, the slope is 0.1%, or is 0.1. It's not 0.1%, it's 0.1. And then the next question is the value of B in the parabolic arc. So eventually we're going to get to A. We're going to solve this, figure out what this whole equation is, but let's start with B. So we've got one equation. There's lots of unknowns in it. We don't know Y, we don't know X, we don't know A, we don't know B. How can we possibly begin to solve this? We know the slope of the uphill grade. What's the slope of the parabolic arc at the point of tangency? You had your hand almost up.
I was just going to say, find the derivative and plug the slope.
Okay, so if you find the derivative, you can find the slope, because the slope is defined as the derivative. But do we know the slope of this curve? What is it? 0.1. Why is it 0.1? What's that? But, all right, so remember, the slope we're given is the slope of this line. And we're looking at the curve. So why is the slope of the parabolic curve equal to the slope of the uphill grade? What's the definition of a point of tangency or a tangent line? At what angle? So it's a line that touches the curve at a single point at the angle or the slope of the line at that point. So if two lines are in tangent, they have to have the same slope at that point. So because we just figured out the slope of this uphill grade, we know that that's the slope of the parabolic arc at that point. And since we know the slope, if we take the derivative, we can set the derivative equation equal to the slope that we know. So the derivative of ax squared plus bx. Taylor, Myers. Where's Taylor? What's the derivative? Excuse me. What's the derivative, enunciate, of ax squared plus bx? Okay. You have your hand up? Right, because the derivative of x squared is 2 times x, right? You multiply by the exponent and then reduce the exponent. So ax squared derivative is 2 times ax. The derivative of bx, if you multiply times the exponent, is 1 times b, and then you reduce the exponent, x to the 0 is 1. So it's 2ax plus b. All right, and we know what dy dx is. That's equal to 0.1. It's equal to 0.1 where? The slope of the parabolic curve is equal to 0.1 where? At the point of tangency. And what's the coordinates for the point of tangency? 0, 0. So we know the value of x. And we know this. And if x is 0, that goes away. So we substitute 0 in for x. We substitute our value of slope in for dy dx. And we can solve for b, as b is equal to 0.1. Okay. Now let me do this. So now we have a parabolic curve that says y is equal to ax squared plus 0.1. And we're going to work our way up to figuring out what a is. But we don't have enough information for that just yet. In order to get that information, we really need to start looking at, at the downhill grade. And so we're given an equation that the downhill grade, the downhill segment, has an equation of y cap equals cx plus d. And the question is, what's the value of c? Right, why? I'm sorry, say that last part again? Right, so in an equation for a line, y is equal to slope times x plus the intercept. We're given the grade is minus 8, so that makes the slope minus 0.08. So c is equal to minus 0.08. All right. So how are we going to find d? Yes, that should be a negative. Thank you. I will fix that and then repost these. All right. So how do we find the value of d? That might work. Because we know a point. We know that when x equals 200, y is equal to minus 6. So we plug in both of those and solve for d. All right. So we'll do that. And yeah, I've dropped that negative sign throughout this entire process. But this is the correct equation, I believe, but I'll double check that to make sure that the negative sign didn't. Yeah. Okay. All right, so now we've got this equation for the downhill line. It's not the downhill arc. It's not the part of the arc. It's this tangent line. So now we want to find the elevation and the actual point of tangency, because we don't know what that point of tangency is. Yes? Yes, it is, because I think if you take 0.08 times 200, I think you're going to end up with 16. And if this is a negative 16 and you bring it over to the other side, it would be plus 16 minus 6. So then D would equal 10. Okay? I can't do that math in my head, but I'm pretty sure that that's what it is. Okay. So at this point, the question becomes, what is that point of tangency and what's the elevation of that point, assuming that the elevation and the slope of the parabolic curve equal the elevation and slope of the downhill line at that point. So this goes back to what we did for the first part of the problem, where we said that the uphill grade and the parabolic curve at that point of tangency have the same slope. And we're saying the same thing here on the downhill grade. So the textbook uses cap and now x bar for the point of tangency and y bar, x bar, y bar for the point of tangency. The y is for the parabolic curve and the y cap is for the downhill grade. So it says that the value of y on the parabolic curve equals the value of y on the downhill grade. The slope of the parabolic curve equals the slope of the downhill grade at the point of tangency. I think I've answered this. Why does this make sense? We've talked about this a couple of times. At that point, a point of tangency, by definition, has the same slope as the point at which it's, as the line at which it's tangent at that point. So we go back to our original equations. The equation for y of x is ax squared plus 0.1x. The equation for the downhill grade is minus 0.08x plus 10. And then we can also do the same thing for the derivatives. The derivative of this equation is 2ax plus 0.1, and the derivative of the downhill grade equation is minus 0.08. So if we solve these two equations, we can figure out the x value and the y value at that point of tangency. So in this case, I'm just combining the equations. We get to this point here for equation 1, ax squared plus 0.18x equals 10, and there's not much more we can do with that because we don't know what x is. In the set of equations for the derivative, when we simplify it, we find out that a times x bar is equal to minus 0.09. Now, I don't know what a is, but I can take this value of ax and plug it in up here, and then I've only got one variable in that equation. Because this is a times x, and I know a times x is minus 0.09. So if we plug that in here, we can solve for x, and it's 111.1 meters. Do you guys know any, question? No. Has anybody ever talked to you, or have you learned anything either here or in your high school about significant figures? Okay. Anybody see a problem here? Say that again? Almost. Almost. Why 2? Which of these values has two significant figures? Does that, 1 and 0? 10 has two significant values. That's arguable, maybe. It might only have one. How many significant figures are in .08? There's only one. Significant zeros to the left don't count. This only has one. That only has one. That has one or two because we don't know if that zero is significant. So this answer really should only have one or two significant figures. One of the issues that I find throughout a lot of textbooks is they don't pay attention to this. They want you to solve an answer and then round it to some reasonable value. But you don't really know what the reasonable value is other than what's based on the data you're given. If you're not going to use the data you're given to determine the significant figures in your answer, there's really no good basis for coming up with a different value, short of really significant long-term engineering experience. Now, this kind of makes sense. I mean, if you're a transportation engineer, you don't want to specify the point of tangency at 110 meters in order to say you've only got two significant figures, because somebody's going to design your road and it's going to be off by a meter, and that could be really important. You know, and if you assume that that's only got one significant figure, and then you specify your point of tangency is 100 meters, now you're off by 11 meters when the design engineer wanted you down here at 111.1. So what this really says to me is this problem should have had a lot more significant figures specified to begin with. So that's an aside. It's one of my personal pet peeves, and I think that significant figures are pretty important, and you've got to abide by them. So when you've got problems like this, give your answer in significant figures, and if there's an issue with it, it's probably because of the significant figures that are given to you to begin with. So this is, where is that point of tangency? It's 111.1 meters down the road. And the elevation we can find by coming back to the equation for the parabolic curve or using the equation for the downhill line. Either one will work because now we have a point of x, and all we need is x in order to find y. Which are you going to choose? Which equation should we use to find the value of y? How about Joe Titleman? Mathematically, we can use either one of these equations to figure out the elevation for the point of tangency. Which one are we going to use?
I would use the boundary.
It's simpler. Okay, that's pretty good reason. There's nothing wrong with making your life a little easier. What's the problem with using this equation in the hat? There's more variables, okay, and we don't know the value of A. But the problem is, let's see. You might be able to do that. I was going to say the problem is that the 206 is not the point of tangency. Well, that's the question, and I'd have to go back and look at the problem statement again. So the question is this point 206 on the downhill grade or on the parabolic curve? From the drawing, I have no idea. I can't tell. Because remember, the point of tangency is only 111 meters over here. It's not 200 meters. So that's not a point of tangency. So whether or not that point is on the downhill grade or on the parabolic curve is unclear to me.
Why would you have 200? I mean,
Well, you know, I'm looking, right, so I'm seeing a parabolic curve and a downhill grade line that someplace there's a point of tangency, and it's probably right around here. this 206 only lies on one of those lines, not both. Or at least we don't know if it lies on both. Say that again?
The laws on both, it's not a point of tangent.
Well, if it lies on both, it must. Well, the point of tangency does lie on both.
But then you have 2 points.
Okay, all right, that's right, and you're not going to have 2 points of tangency. And since we know the point of tangency is only at 111 meters, that can't be a point of tangency. So you could make the argument that it lies on the parabolic curve. And if that's true, you could plug it in here and solve for A. We don't know if that's true. And maybe if you reread the problem statement, it might be a little clearer, and it might tell you that. But assuming that we don't know what A is, we do know what X is, and so we can use this equation to solve for Y, the elevation of the point of tangency, and it's 1.11 meters. So now what we want to do, now we're going to go and find the value of A, because now we have the point of tangency which lies on both curves, and we can solve for the value of A. And in this case, we just plug these values in and we come up with 8.10 times 10 to the minus 4. I think the textbook gives you the answer expressed this way, and there's nothing wrong with that. I'm a real big fan of significant or scientific notation because it takes away all the ambiguity about significant figures. If you write a number like this, that's significant. 8.10 is 3 significant figures. This is 3 significant figures as well. It's a little harder to read. So anyway, you can do it either way. So that's the value of A. So the equation for the parabolic curve is minus 8.1 times 10 to the minus 4x squared plus 0.1x. So a matter of a little bit of use of derivatives, a little bit of algebra, and we can solve some of these more complex problems. One thing that you're going to find, if you haven't figured this out already, is you're often going to be faced with a problem, and you read it, and you don't know where to start. I don't think this solution was necessarily intuitive. If I had given you this question and said, give me, define that parabolic curve equation, I would suspect most people would have a really hard time doing that because it's not a clear starting point. One of the things you really have to learn and get comfortable with is when you have a problem and it's not clear what direction to go in order to solve that problem, try something. See how much information you can get. And as you start writing some of the equations and start solving some of the problem, the next steps may come to you. They may become more obvious. And if you get to the point where it's a dead end, that's okay. Go back and start over. I see, in my opinion, too many students who feel like they've got to have the entire solution envisioned in their head before they start putting pencil to paper. And that's not always going to be possible. Sometimes you just got to start writing and let things come to you as you write. So that's my advice for the day. Any questions, comments, concerns, issues? All right, I'll see you Monday.